All right, so this is our last talk for the um, for this first part of the Summer Institute, focusing on um, the skills that you need to use advanced cyber infrastructure if you are not a programmer. So, table of contents will give you a little bit of an introduction, and then we're going to go through a bunch of the different tools that are available. Head and tail, paste, sort, split, grep, sed, awk, and then look at a few case studies where we combine a few of these, and then wrap up with some conclusions. Most of these, I'm going to say, except for sed and awk, are pretty simple tools. You may already be familiar with them, but I think it's worthwhile to have a review to get everybody up to speed. So with these new series of talks that I put together for the end users or non-programmers, I always like to start off with a little bit of context. You know, who is this session intended for? Why are we doing this? So I'm going to say this session, it's intended for anybody who needs to post-process text files to extract runtimes or results or information about hardware used in the calculations. If you need to construct workflows, prepare high throughput computing workloads. You know, I know Marty just got done talking about high throughput computing. And if you could, you know, put together a simple script to generate, you know, your whole array of starting conditions for your calculations, these tools will really come in handy. Sometimes, well, I'm not going to say sometimes, very, very often, you need to pre-process data to get it into the correct format. I could think of very few times that I've downloaded a data set and, you know, for my purposes, that it was all ready to go. And this is, you know, outside of, say, the canned data sets that are distributed with certain R and Python packages. So the Linux environment gives you a wide range of tools for sorting and splitting and manipulating files, and also tools for extracting content based on location, say like the line number or the value. So we're going to go through a bunch of these pretty quickly. Split, head, tail, awk, sed, grep, and paste. A few of these, awk and sed, are very, very, very complex tools. There are, and I'll show some examples of this, but there are extensive discussion forums for awk and sed. There are some real enthusiasts out there, and these are very powerful tools. But we're just going to look at some of the basics, things that I feel are going to be of immediate use. So again, if you want to follow along with any of these examples, go into the repo, either the Summer Institute repo, you know, follow down to my presentation, or in that complex repo. So before you start learning a new tool or a new skill, and this is a question I always ask myself, do I really need to learn something else? I just feel that, you know, life has become, you know, so complicated over the years. There's so much to know, so much to do. You know, I was just recently on a vacation, a bit of a college reunion. One of the guys had rented a Tesla, which is a wonderful car, and we're trying to start it one day, and it's asking us for a PIN number. So it seems like, you know, as we get more technology, there are more complexities. But I'm going to try to make the case that these tools are going to be so helpful and so useful that you will be glad that you took a little bit of time to learn them. So just about everything that we're going to be doing, you, in theory, could do it by hand, but these processes are going to be time-consuming and tedious, and I'm going to say, worst of all, error-prone. It's more likely that you're going to cut and paste something and make a mistake, and then, you know, really set back your research or your science. And as far as being error-prone, you know, tedious, this is especially true for something that needs to be done many, many, many times. And this ties in well to the high-throughput computing, since you might be running, say, a given calculation for 100 or 1,000 or 10,000 or more, more different conditions, but essentially doing the same kind of work on that data. So obviously, we'd like to automate the process. Sometimes this requires the development of relatively complex parsers. In fact, I'm running into this in one of my own projects. I'm going to say are beyond the ability of non-programmers to write. But for much of what you need to do, I think you're going to find that these Linux utilities are sufficient. And I've mentioned this a few times already. We've got some hands-on examples. You could either do them now as we go along, or feel free to do these after we're done. Work on it on your own. I think they're pretty simple, pretty straightforward. If you look in those directories, you'll see a few input files, and you'll see an obviously named file with the commands. So that command file, we don't necessarily mean for you to run all of those commands, to just run that script. But if you want to cut and paste the commands out of there and run them. So when you try to master these tools, I'm going to make a few suggestions. First of all, deliberately introduce errors. Leave out quotes or commas or semicolons, or do other things to break the syntax to see what happens. I feel that I'm always more comfortable with a new tool when I've had a chance to break it. Take the examples that I have. Maybe introduce new features. Look at things that we haven't covered. Go into the man page, see if there are any additional options you want to play around with. Try chaining these tools together to create more complex workflows, and this is what we do in the case studies toward the end of this presentation. And then finally, and this is what I'm hoping you're going to do in real life, is take these tools and apply them to your own use cases, to your own research. So with that, we're going to jump into our first tool. And before I do, are there any questions? And Susan, Cindy, and others who are monitoring Slack, let me know if anything comes in.
Will do.
Alrighty. So we're going to start off with head and tail. I'm guessing this is a tool that many of you are familiar with, probably the what I'm going to consider the easiest text processing tool to work with. Head, by default, just gives you the first 10 lines of a file, and tail is going to give you the last 10 lines of a file. If you go into that head tail directory within my repo, you'll see the commands in the command file for executing this, along with the file.txt. So pretty straightforward. As you might expect, you can override the default and specify the number of output lines. So in this case, if I want to look at the first 7 lines of the file, I might do a head-n7. So the -n followed by the number is the number of lines that you're going to get. For tail, similarly, -n7, and you're going to get the last 7 lines of the file. And I didn't know this until I started putting together this presentation. But we can also tune this a little bit more so that we list all but the last num lines to be output, or the first, or from a given position onward. So I know that sounds a little garbled when I say it out loud, but let's look at a specific example. Here we're running head-n, and this time with -15 instead of 15. So I don't want to see the first 15 lines. I basically want to see everything except the last 15 lines. And then for tail, in this case, I want to see all of the lines from 16 onward. These options, I don't use them. I don't use them nearly as often. It's just a sort of like a bare head or tail with a given number of lines. But depending on the kind of file processing that you're doing, you might find these useful. Okay, I'm going to move on to paste, which I think is a pretty simple tool and yet really, really convenient. What paste is going to do is it's going to merge the lines of a file. So it combines 2 or more files line by line. And by default, The the records, sorry, the fields are going to be separated by tabs, but you can override that using the -D option. Before I discovered paste, I was doing a lot of um, printing the output, say using cat, doing a physical and copy paste with my mouse, pasting these lines into a spreadsheet, and then dumping back to a file. But this is going to be much more convenient. You won't have to go back and forth. So I put together an example here. Again, this will be found in the paste subdirectory. So I have a file called fruits.txt, apple, banana, and grape, and another file called colors, red, yellow, purple. And if I wanted to combine these so that I get a single file with the with the lines of each of these two files combined, I could just do a paste. In this case, paste fruits.txt, colors.txt, and now I get, for my first three records, apple red, banana yellow, grape purple. To show how you can change the delimiter, the example on the right-hand side is exactly the same, except here I use the -D option, and I specified that a comma would be the delimiter. So now I have apple, comma, red, banana, comma, yellow, grape, comma, purple. And this would be really convenient if you wanted to generate a file, a CSV file, something that's going to be automatically opened by Excel. Okay, going on to the onto the next tool. Yeah, getting just a little bit more complicated. A little more complicated. Sorting is just one of the most useful things we can do. It comes up in all sorts of contexts. I find it. I find that I do this a lot in my own workflows. So as you would expect, Linux provides a sort utility. So let's say I'm starting with a file. I'm calling it unsorted1.txt, and it just has a list of fruits. Banana, apple, grape, pear, apple, peach, banana, grape, orange. And you'll notice that some of them are capitalized, some of them are not. So if I do a sort, generally, I'm going to get the result that we expect, and that's that the case is ignored. So you'll see that when I sort this, I have apple, apple, both lowercase, banana, banana, both in uppercase, and so on and so on. So we are going through A through P. If we have numbers in there, that the sorting is going to be based on the ASCII lexicographical ordering. Now, if you have this environment variable set, lc underscore all, if I set that equal to C, now when I do a sorting, I'm going to get a strict ASCII ordering, in which case the capital letters occur before the lowercase letters. So in this case, we've got but banana and grape appearing before apple, orange, peach, and pear, even though you would normally think of banana and grape as being as coming, say, after the A's. If you ever, the main reason I'm bringing this up is by default you're probably going to have that LC all environment variable not set. But if you see any unusual or unexpected results, you may want to double check and make sure that it's set or unset as appropriate. Okay, sort also gives us a lot more power when we have multiple fields in each record. So we can use the K option to, along with the N option, to decide to sort on a particular column, and if we use -N to sort by numeric value. So let's take a look at another file. I could label this one unsorted2.txt, and in there it's just each record is just a fruit, a number. Let's say it's an age, and a food. So I was thinking, let's say we have 5 people. We're listing their favorite fruit, their age, and say their favorite food. So if I wanted to sort on that third column, instead of sorting right from the beginning, I could do -K3. So the -K means that I'm going to be selecting a column. The 3 means that I'm going to be selecting the third column. And in this case, you could see that the sorting was um, done alphabetically on that last column. So we've got hot dog, pizza, popcorn, pretzel, taco. Now let's say we wanted to sort on the age. If I did a sort -K2 unsorted 2.txt, the results are going to be probably not what is expecting. You'll see that we go 12, 17, 23, 35, 6, and that's because we were using the ASCII ordering for those characters. I should have put this into the presentation. I'll be sure to add this next time. But the ASCII ordering is a listing of 256 characters, or originally 256. It's being expanded beyond that to allow multi-byte characters. And it gives the ordering the standard ordering for the letters, the numbers, punctuation marks, and a few special characters. So here it was being done lexicographically. So 1 comes before 2, 2 comes before 3, 3 comes before 6, and that's where we're getting this, what may look like a, unexpected ordering. If we want to sort on that column and have the values interpreted as numbers, we can just add in the -n flag. And now in this case, we're getting what we expected. Um, we've sorted the data, say by the person's age. So we've got 6, 12, 17, 23, and 35. And then sort can also be restricted to listing unique values by specifying the -u option. And this is something that I find is really, really handy. You may have done this in Excel or other spreadsheet programs already, where you see that there are a lot of fields that are being repeated, but you just want the unique values. So for myself, I'm a really avid hiker and what we call peak bagger. I like to climb lots of different mountains, and I actually maintain a spreadsheet with all of my peaks and some of the details, including the states. And sometimes I might just want to see, hey, what are all the states that I had climbed a mountain in? It's easy enough to do in a spreadsheet, but if I had everything in a file on Linux system, I'd want to use the sort command. So we're going to go back to original file unsorted1.txt. Again, we see have a random listing of fruits. If I sort it, then I'm going to see apple, apple, banana, banana, grape, grape, orange, pear, orange, peach, pear. And if I wanted to know just what are the unique values, I could do a sort -u, and now I've listed it down to just the unique entries: the apple, banana, grape, orange, peach, pear. What was I thinking? One point here. Oh, how to put? You need to make sure that you. I guess there's no way to do this without sorting. But I'm going to say if the data was not sorted, using the unique option wouldn't work, because I believe that after you sort, the -u option looks for repeated values in the list. And with that, I'm going to wrap up with sort. Again, do we have any questions so far? And if I hear silence for a few more seconds, I'll just assume that I can move on.
Yeah, but I don't see any in on our channels. You're good.
Okay. All right. Thanks. So, like I said, feel free to ask questions. We want this to be pretty interactive. All right. So now we're going to get just a little more complicated, and we've been using mostly toy problems. I think it's easier to illustrate with things like lists of foods and fruits and columns of numbers. But I'm going to actually show an example from real application I worked on, where I had to process some large genomic files. And what I needed to do was what was to split those into chunks that we can work on separately. So if you go into the split directory, you're going to see a genome.fasta. And if I just do split with no other arguments, I'm going to get a bunch of files. By default, chunks of 1,000 lines each. And the naming convention is kind of obtuse. We're going to start with XAA, XAB, XAC, so on and so on. When we get through to the Z's, XAZ, next file I believe will be XBA, XBB, XBC. I don't know what happens if you have more than 26 squared files, but I believe that split will handle it appropriately. So split, like all of these other tools, comes with a lot of handy options. By default, we probably don't want to split into chunks of 2,000. Let's say we have in mind that we, want to split the file, but maybe limit it to about 5 chunks. So in this case, I could do I could use -L, which I believe is abbreviation for number of lines. In this case, I use -L 2000, followed by genome.fasta. And then, so that we don't have that, kind of obscure naming convention, I can specify a prefix. So here, my prefix is genome underscore, and that's going to be used in the file naming instead of X. So now we're going to get genome AA, genome AB, genome AC, and so on. And you can see, as expected, that the data was broken into 2,000 line chunks. The last one just gets truncated. It just gets truncated a little bit, since there weren't 2,000 lines left. Okay, here's where things get a little more complicated, and we're going to come back and visit this at the end of the presentation. There are some files that have a really well-defined structure. So if any of you are coming from bioinformatics backgrounds, you're probably familiar with FASTA files. They're used for genomics data, both DNA and RNA sequences, also protein or amino acid sequences. When we run split, the default record separator, basically how do we know when we've moved on to a new line, may lead to some undesired behavior. In this case, we want to keep the annotation for each of these for each of the records in the FASTA file together. So I did this, and the format of the FASTA file is that you have an annotation line. It's going to start with a greater than sign and a bunch of annotation, and then you're going to have one or more lines containing the sequence data. If I look at this case, it is amino acid sequences. So what I can do is I can split on a different record separator, and that's what I'm going to do in this next example. So here I'm going to split into groups of 200. So this is not going to be 200 lines, but essentially 200 of these records. And then with the -T and specifying greater than sign in quotes, I'm saying I'm going to make my delimiter the greater than sign instead of the new line. And now if I look at the head of each of those files, we'll see that they start off with the annotation line, but with one little quirk. And you'll notice for the second line and the first line of the second and the third file that we're missing that greater than sign. And that's really important, because if we don't have that, all of my bioinformatics applications which are expecting a particular FASTA format are going to break. They're not going to recognize that as annotation because we do not have that greater than sign in the first position. But a little bit later on, I'm going to show how we can fix this. So basically what happens is the record separator is consumed. So it recognizes separator, but it's not printed as part of the output. All right, any questions so far on header tail, paste, sort, split? And I'm going to take silence to mean that there is nothing. And we will move on. We're going to look at a couple of examples that are just a little more complicated. And I think we're going to finish up a little early today. So Marty went a bit late. I'll probably get us back on time, or maybe use that use that time at the end of the session for y'all to work through the examples, and I could be here to answer questions. So now we're beginning to get into gradually into some more complicated tools. And we're going to be talking about grep. And what grep does is, hold on a sec. So I just had a helicopter going overhead. So at its simplest, grep is going to return all the lines in a file containing the search string. Keep in mind that upper and lower case letters are different characters, and if you want to ignore case, you'll have to use the -I flag to make the matches case insensitive. So I've got another file here, kind of sticking with my theme of fruits. This will be in the grep directory. So we look at the contents. Each row has 3 fruits. We start off with apple, banana, pear, cherry, banana, peach. And I threw in a few capitalizations. So as we get about halfway down, you'll see there's a apple, capital B, banana, pear, and a cherry, capital B, banana, peach. So these lines are going to be distinct from the first 2 lines if we, unless we ignore case. So on the right-hand side, you could see a couple of grep examples. Here I'm doing grep banana on file1.txt. Banana is my search string, and then I get those 2 top lines, apple, banana, pear, cherry, banana, peach. On the next line, I'm using capital banana as my search string, and you'll see the results are different. I'm just getting those 2 lines where we had a capital B banana. So apple or cherry, capital B banana, peach or pear or peach. If I wanted to ignore the case, I'm just going to use the -I flag. And now I get banana, whether it's little b banana or big B banana. This is a really cool feature of grep that I've used many times, and that is listing a line or lines that occur before or after the matching line. So sometimes there may be, when I'm parsing output from programs, there's, say, a fixed line that I know is in there. But the output line could vary. The names and the numbers would vary, and it would be hard to search on that line. So I might say, in my output file, there's a line that I know is always going to be there. Program output, for example. And I know that the line that I want is, say, 3 lines after that. So by using these -A and the -B patterns, I can zero in on those lines without actually knowing what the content is, just knowing that those lines occur close, or sorry, occur at a known relative position to the lines that I'm searching on. So we're going to go back to our fruit file again. This time I'm going to search for kumquat, but I'm also going to list the 3 lines that appear before the kumquat match. So now I'm going to get, and I've highlighted in red so it jumps out a little bit. You can see the 4th line of output is pear, kumquat, grape, but then we have those 3 preceding lines. Similarly, I can print lines after a match. So in this case, I'm specifying -A2. The A stands for after, the B stands for before, and now we get pear, kumquat, grape as our first line of output, and then the following 2 lines in that file. And you may be wondering what happens if we have multiple matches. So let's say kumquat appeared 2 or 3 or more times. you're going to see that the lines that occur before or after the match will be printed for every match. But this would be a great experiment to go back, play around with this, and see what happens if there's, say overlap. If there's, maybe only 3 lines between the matches for kumquat, but you specify, dash B or dash A with the number that's larger. So it's always nice to play around with those end cases. Another cool feature of grep is that you can do what we call an inverted match, and that is to print lines that do not match a pattern. So going back to our fruit examples, I have a couple of files in this grep directory, file 1 and file 2. Each of them have lists of lists of fruits. And if I do a grep lime star, so basically search for lime in all of those text files, I'm going to get the matches for each file. So I see file 1 has 2 lines, orange, lemon, lime, grape, guava, lime. File 2 has 3 lines, orange, lemon, lime, pear, lime, grape, grape, guava, lime. Now, if I want to get all of the lines that do not contain the match, I could use the -v flag in order to invert the search. And now if you look at the results, you'll see that my output is all of the lines that do not contain a lime. Okay, we could also, sometimes we just want to know, instead of getting the actual output, we want to know how many times we have a match in each file, or just whether or not that file contains the match. So again, if I did that grep lime star, I'll get the 2 matching lines from file 1, the 3 matching lines from file 2. If I do a grep -c lime star, I'm going to get counts. So in this case, it shows us that file 1.txt had 2 matching lines and file 3.txt had 3 matching lines. Okay, if I look on the right, this gives us listings of files that contain the match. So in this case, I'm going to, I want to see which files contain kumquat. I do -l for list. We find that file 1.txt is a match. But if I want to invert that, I could use -L kumquat, and now I'm seeing all of the files that do not contain the match. So a lot of options in grep. I'm going to go into one more example. Grep, the real power of grep is when we get into something called regular expressions. These are patterns for expressing sequences of characters. It gets a little more complex. We could do an entire day on regular expressions, but we won't. If anybody's interested, I can follow up later and point you to some good resources. But I'll give you just a few of the useful features. So we can use something called anchors, which says that I'm looking for a match at the beginning or at the end of a line. So again, going back to our fruit example, if I do a grep pair in file 1.txt, I'll see those 4 lines that have a match. Now let's say though, I only want to see the lines that start with pair. So in this case, I could use that caret character as an anchor. And now in quotes, I have within single quotes, caret pair. This means I'm only looking for lines that begin with pair. In this case, we get our pear kumquat grape, our pear peach kiwi. Sometimes we want to look for matches at the end of the line. Here I can use the dollar anchor, which is going to appear at the end of my quoted string. In this case, quote pair dollar quote. And now I just see those 2 lines where pair appears at the end. Now, if pair had been the middle column for any of those rows, neither of these matches, neither of these grep commands would have caught it because it appears neither at the beginning nor at the end. And if I use these together, say quote caret pair dollar quote, that's going to mean that pair needs to match at the beginning or the end, or essentially that the entire line, except for the new line character, consists just of that content. So these can be combined. Right. Any questions so far on grep? Right. If not, I am going to move on to sed and awk, and these tools get a little more complicated. So sed, it's a stream editor for filtering and transforming text. It is an extremely powerful editor that operates on a stream of data. So what this means is we're not taking the entire file and reading it to memory and editing it. Basically, we're streaming through the data line by line. What's nice about this is that sed could be used for extremely, extremely large files. So let's say that you need to do some sort of a transformation on a file that has a million lines or even a billion lines. It would not be practical to open that up, say in Nano or VI or Emacs. You would probably run out of memory. This is where sed is going to be handy. It also allows you to automate and script the processing. So when I said earlier that we could spend an entire day on grep, we could spend probably an entire week on sed and awk. And in fact, there is a famous O'Reilly book named Sed and awk that probably goes into much more detail than most people would ever want. If you want to know more about sed, I'm going to say two great online resources are the ones that I provided here, sed.sourceforge.net, and also go into the tutorials, and you will see some sed examples that I found absolutely mind-boggling, that I would probably have to spend hours reading to fully understand. Fortunately, we do not need to do that. We do not need to go that far now. I'm going to show you what I think are the most important features. So starting off with applying a substitution to each line of a file. So again, while some of these could be done, say with a global replace in a traditional editor like VI or Emacs, sed has the advantage that it is scripted and the entire file does not need to fit into memory. So most of the time when you use sed, it's going to be to do these replacements, either a single replacement. So in the first line I have here in the gray box, in quotes, I have s slash replace the first occurrence of this slash with this slash, and then closing quote. And I just realized, and I'm going to fix this later, do not cut and paste this particular command from my presentation. One of the straight quotes got converted to a stylized quote, so that's not going to work. But it is correct in the commands file. And then sometimes you want to do the replacement for every occurrence within the line. And to do that, we're just going to add the G flag after the third slash. And then this is followed by the name of the input file. So to make this a little more concrete, we're going to go into the sed directory, and you're going to see a file named file1.txt. And in this case, we want to take, and the coloring, the green, the red, and the yellow for for the anchors and for the global replacement. I just put that in for convenience. In real life, there's everything is going to be, and everything will be in black. So here, I wanted to go into that file, file1, and I wanted to replace every occurrence of pair with 4 x's. So if I do that, you'll see with these 5 lines, that going through the first 3 lines, we did our replacements, did all of the replacements. You'll notice though, in the last 2 lines, that the second occurrence of pair was not was not replaced. And again, that's because I did not use the global quantifier. If I go down to the second example, still in the first column, the only difference is that I added the -g flag at the end. So that says I'm going to do the global replace. Now when I run this, we'll see that every occurrence of pair in every line has been replaced. We talked about carets with grep, sorry, carets and dollars or anchors. They can also be used in sed. So in this case, I added that caret in the first part of the expression. So now I have caret pair slash xxxx, and that means I'm only going to replace pair with xxx if it occurs at the start of the line. And then if I want to do the replacement at the end of the line, I can use dollar. So now I have pair dollar, and now only that match at the end of the line is going to be replaced. Okay, another thing, I'm going to say this is probably the second most comfortable thing, second most common thing you're going to do with sed is to print out specific lines. I find this is really, really handy. In the past, I would do this with combinations of, say, head and tail, where I would run a head command and then use tail to get just the end of the head output. This is a little more reliable, a little less error prone. So in this case, I'm showing the syntax for printing the 5th line. So we're looking at file2.txt. Something doesn't seem quite right there. I'm sorry, there is a typo in there. That's supposed to be a 3. I cut and paste incorrectly. So if I have in quotes there, quote 3 quote p, the p means that we're going to print, and we get this is line 3. I can specify a range of lines. Here in the quotes, I have 3, 5, which means that I'm going to get lines 3 through 5. And then we can also specify a stride. So in this case, I'm going to be printing every 3rd line starting at line 2. So within the quotes, after the first quote, the 2 means where I'm going to be starting. The tilde 3 means that it's going to be every 3rd line. Again, the p means that we're going to print. So we're seeing lines 2, line 5, and line 8. There's just one gotcha that you need to keep in mind when you're working with sed. Like all of the other Linux tools we're working with, the output can be written to standard out. It's written to standard out, or it can be redirected to a file. But there's one gotcha, and that's that sed is a stream editor going through the file line by line rather than storing the memory. Redirecting the output to the original file is not going to work. You're going to need to write a temporary file, or you could even better, you could use the -i option to do an edit in place. Of course, behind the scenes, there's going to be some internal temporary file that sed is using. So let's say we want to look at a short file here. We're going to take the first 2 lines of file 1, pipe that into file3.txt, just so we have a shorter file to work with. And now I'm going to do the substitution, replace pair with xxxx on file 3, and then redirect that into file 3. And when I do a cat on that file, we see that we're going to have no output. So essentially, I took the output, I overwrote the file as we're working on it, and in which case we get nothing. So there's a better way to do this is to use the -i option so that we could do the edit in place. So here we have a sed -i, the line for our substitution in the file. And now when we do this, we see that file 3 actually was what was edited in place. And the only reason that I didn't edit this command here, the head to file1.txt, piping that in file 3, is so that it would not overwrite the example. All right, so we have one more tool we're going to look at. Any questions about sed before we proceed?
Bob, we do.
Yes.
From Karen. Does a grep for caret pair $ find lines with pair at the beginning or the end, or lines with pair at the beginning and the end? And you'll find this in the main room.
Yes, yes. So what's going to happen is for that, you're only going to get ooh, I need to double check that. But I believe what's going to happen is if you have the caret and then match and then the dollar, you're only going to get lines that contain exactly that. So, if you give me a second, I'm going to stop sharing my screen and I will double check that. Let me go ahead and share again. Let me make this a little bit bigger. Okay, so there we go. That's looking for pair at the beginning and pair at the end. And let's see when we combine them. Okay, yep, it did exactly what I thought. It's going to give you that's essentially going to be an exact match. So it's not so with caret, pair, dollar, we don't get all of the lines with pair in the beginning plus all of the lines with pair at the end. We only get lines where it starts with pair, just though that sequence 4 characters and ends with it. So if we wanted to get all of the lines where it appears at the beginning or at the end, we would either have to do this as 2 grep commands, or we need to write a more complex regular expression that has the that includes the 2 options.
So Bob, does egrep work if you have multiple? I haven't tried it.
I haven't tried it either. I don't know if egrep is actually supported anymore. I thought that egrep and fgrep, that all the functionality has been rolled into grep over the years. But I need to double check. And Susan, do we have any more questions?
No, Bob, we don't.
Alrighty, great. Thanks for the question, Karen. All right, I'm going to go back to the presentation. Oh, where am I? Okay, let's go back into presentation mode. Okay, so we have one more tool that we're going to cover, and then we are going to get into a few case studies to see how you might actually use these, or how I used them in the past. Okay, awk is another really, really powerful tool. You saw this book cover already. This is the famous Sed and Awk book by Aho, Weinberger, and Kernighan. Awk is a powerful text processing tool named after its 3 creators. Lots and lots of capabilities, just as mind-boggling as Sed when you go really, really deep. But we're going to, again, restrict ourselves to just a few of the simple and commonly used ones, like But like I said, we could spend a lot of time in this. In fact, with a little thought, I could probably put together a week-long workshop on set and awk, but I doubt very few people who would wanna sit through that. As you would expect, there are a lot of great online resources. These are a couple that I thought were particularly useful. All right, so awk is a pattern and scanning processing language. So awk, like said, is going to operate on the file one line at a time. It's going to split it into fields referenced by position, with the numbering beginning with 1 and going onward. I think $0 is like a lot of the other Linux utilities and C programs, reserved for the name of the program itself. If you want to access the last field, there's a special variable, NF, where NF is the number of fields. And the most common use of awk is to print selected fields from each line. So I put together a file in the awk directory, and I kind of made a guess for some of the folks who are leading the Summer Institute. So for myself, Cindy, Mary, and Susan, and I kind of guessed what our favorite animal, food, fruit, and color is. So you can see, for example, for myself, I listed dog, I love meatloaf, I love bananas, my favorite color is blue, so on for the others. But let's say that I just wanted to extract some of that information. I just want that first column, first column, third column, and the last column. So our names, our favorite food, and our favorite colors. So we could use awk, and I'm showing what is probably going to be your go-to awk feature 90+% of the time, just to print out those columns. So I start off with awk, and then in single quotes and within braces, I have my print statement. I'm going to say print, and then $1, $3, $NF. I could have also done that as $1, $3, $5, but I wanted to demonstrate the NF variable. So in this case, we just get those 3 columns: Bob Meatloaf blue, Cindy Pizza purple, and so on. So awk can also take a search pattern, and it can include other text in the output. So let's say I wanted to, instead of just a listing of names and favorite food, I wanted to add some additional text in there, maybe format this a little bit nicer. So in this case, my statement within the quotes and the braces, it's going to be print $1, and then I have a string, double quoted. Favorite food is, and then $3, and then we'll have this operate on people.txt. So now we find Bob favorite food is meatloaf, Cindy favorite food is pizza, and so on. Now, if I wanted to limit that to matching lines, I could provide patterns just like I would for grep or for sed. So a lot of what you learn for one of these tools is going to be easily carried over to the others. In this case, I'm going to start off within my single quotes. I have /pizza/, so this is the match that I'm looking for, and then that's followed by the print statement. So I'm going to get just the lines that contain pizza, and then I will print the name and the food. By default, awk uses white space as the delimiter, but as you might expect, this can be changed. We have a -F option, and I find this is really handy when I'm working with comma-separated value files. So let's say I have a file called states.txt, and in this I list the state, the capital, the state bird, and the state flower. Now, one thing that makes this a little more complicated is that we have embedded spaces. So you'll see there is a valley quail, a ruffed grouse, an eastern bluebird, a mountain laurel. So um, if I use awk with the with the standard or the default white space delimiter, this isn't going to get this. The lines aren't going to be parsed the way I expect. So, for example, that first line will be split into two fields: California, comma Sacramento, comma Valley. Then we have a white space. So now my second field is going to be quail, comma poppy. So what I could do instead is with that dash capital F option, I could say I want to split on a comma instead of a white space. And like I did in the previous example, I added in a little extra text to make this, make the output prettier. So I've got my print $1, state bird is $3. In this case, we get California state bird is valley quail, Texas state bird is mockingbird, and so on. And this is something that I only learned fairly recently. One of my colleagues, Andy Getz, who you heard from, I believe, yesterday, told me that you could use awk to do some basic mathematics. In this case, let's say I have text files with white space separated numbers. I could actually do arithmetic on that. So the expressions are getting a little more complicated, but within the quotes and the curly braces, I have sum equals $1 plus $2. I separate everything with semicolons, just like if I was a C or C+ programmer. Then I define the product as $1 times $2. And now I'm going to print out the two values along with the sum and the sum of the product. So what we see is, first row, 1.1, 2.2, the sum is 3.3, and the product is 2.42, and similarly for the next line. This was another thing that surprised me a little bit, and that is awk has built-in square root and logarithm and exponentiation and trigonometric functions, along with random number generation. So let's say this time I wanted to calculate sines and cosines. I can then assign the result of sine of $1 to a variable called sine1, cosine of $2, I'm going to assign to cos2, and then I'll print out $1, $2, the result of the variable sine1, result of a variable cosine 2. And here we see the same results except with sines and cosines instead of numbers. And then just one more line showing how you can calculate logarithms and square roots. So this is a really handy feature if you need to automate sort of spreadsheet like functionality. So instead of having to paste things, take this data, paste into a spreadsheet, figuring out what the delimiter is and so on, doing that manually each time, you could work directly on your tables and numbers. And then one last feature of awk, and this is starting with the begin and end features. Sometimes you want to print something out just once, but awk by default is going to apply everything to every line of code. So here, what I did was I used the begin statement. So see, after the first single quote, I have begin, and then in braces, I first define a constant. I'm going to say that pi is 3.14159, so that I can use that continuously throughout the rest of the execution. And then I'm going to print a header line, x, y, sine of x, cosine of y. Then after that, it's actually broken across a few lines. I'm doing what I was doing before, except I'm now multiplying the multiplying number of radians by pi. So I calculate sine of the first field times pi, cosine of the second field times pi, and now introduce yet one more feature. a printf so that I can specify the length of the field and the number of significant digits. And when I run all of this, I get a much nicer output. So compared to what I had here, sorry, in the middle, which is a little hard to read, instead I have my headers and I have everything evenly spaced. And again, we're just scratching the surface with awk. With that, we are almost running out of time. In fact, I thought I was going to make up some time, but I'm not. But I'll be done in the next couple of minutes. So before I go on, any questions? All right. Or if not, I'm just going to show you a few case studies. These get a little more complicated, but they're real life case studies. And most of these were taken from one of the tasks I have here at SCSC is that whenever we get a new supercomputer, they'll turn it over to me for anywhere from 3 days to a week to just load up the entire system with jobs, doing a stress testing, seeing if there are any performance issues or bad nodes or so on. So I end up running sometimes tens of thousands of individual jobs, a mix of applications. And having these scripts and using these tools made it so much easier for me to process all of the output and track down the problems. So I mentioned this already. Here in the first paragraph that we do this, we do this reliability testing. One of the codes that we run is HPL, or high performance LinPack. Here we're not doing any real science. We're just solving a big standard linear algebra problem, keeping track of which node it ran on, what the runtime was, and whether or not it passed. So when you do floating point arithmetic, you don't you get some rounding errors. And what the HPL benchmark does is it confirms that your solution to the linear algebra problem matches what's expected to within a given tolerance. So there are going to be 3 fields that I need to extract out of these output files. Where I have the 3 dots, near the top and down toward the bottom, that's where there's additional output. I just restricted this to the lines we're really interested in. First field highlighted in red, VGR-10-01. That is the name of a node, a compute node on the Voyager supercomputer. It's our specialized AI system. We also have the time field. I want to know how long each run took. And then down at the bottom, we're going to have an output that says either pass or fail. So what I would like to do for these thousands and thousands of HPL runs is extract those 3 fields. Excuse me one moment. Okay. So what I did was I put together a script that would iterate over all of these HPL output files and capture the information that we need. Don't worry if I go through this a little bit fast. You could kind of check it on your own. I believe during Andy's talk in Intermediate Linux yesterday, you saw the use of backticks for capture and output. So what I did is I start off, I'm going to print a header, node, time, whether or not tests pass or whether or not they failed. So that's the P and F columns. I'm then going to do a loop over all of the files that match this pattern, output.hpl star. And then within the loop, I know that the node name is that first line of the file. So I'm going to execute head -1 file. That way I get the node name from the first line of the file. Then I want to extract the time. Here I'm looking for the line using grep that contains WR12, R2, R4. That's kind of an internal code for the HPL benchmarks. I'm then going to take the results of that line and I'm going to pipe it through awk so that I can extract the 6th field. Then I want to find the number of past tests. So that's where I have the npass equals, and then backticks grep past file. Pipe that through wc-l. Reason we have to do that is we didn't do it in our particular case, but sometimes you could do multiple tests within a single run. We also get the number of fails, and then finally we print that all out. And I just want to add that when we did the testing, none of the hardware on Voyager failed the HPL test. I just added some failure conditions to our to the files in the repo for illustrative purposes. So when I did this, I executed it again using this combination of head, grep, awk, and wc. I was able to generate this nice little table listing nodes, runtimes, and pass or fails. Another example that this was during the reliability testing for Voyager. We were doing BERT benchmarks. So BERT is a natural language processing framework. In this case, each of the nodes had 8 of these specialized what we call Gaudi cards, and we wanted to make sure that they're all working correctly and giving correct results. So again, I'm just highlighting part of the code here. At the top, we have the node name. This kind of cryptic string here, 0000, 1B 00.1 indicates the card within the node. T before and T after are Linux times. To essentially what we call epoch time, the number of seconds from January 1st, 1970. And then there were 2 results that I wanted to extract. Here in the correct answers line, we wanted to make sure that we were getting the correct answer at least 85% of the time. And we were also interested in the rate. How many sentences could BERT process per second? So this is a little more complicated, but we start off. We get the node from the first line. We get the card from that second line where we're grepping for AIP, open paren, pipe that through awk. Similarly, we use grep and awk to get the start and the end times. Combinations of grep tail and awk to get the last instance for the correct answer and the achieved sentences. The reason we had to do that is these lines here, correct answers and achieved sentences, are printed many times as the model is trained, and we're just interested in the very last instance of that. When we're beginning and the model hasn't yet been trained, the correct answer rate is close to 0, and it slowly grows over time. And then I added in some math here to calculate the difference between the ending and the start times, and we dump everything out. And then once we do that, we'll get a nice table listing nodes, cards, so we can distinguish between the 8 cards in each of those nodes, the percentage success, the number of sentences that we process per second, and then finally T was the runtime. And then the last example I'm going to show, getting back to the FASTA file, where we had that issue with losing the delimiter. After I split, I just went through all of the genome files, ran a sed command on them. So basically, if a line starts with lowercase sp, we replace it with greater than sign sp. And now when I look at the first line of each of those files, we see that the annotation line is correct. So that is it. I know I threw a lot of stuff at you. Hopefully, though, you're going to find this to be really useful for automating your workflows and limiting the amount of time that you need to spend going into files and manually pulling out results. So it's going to make your life a lot easier. It's going to improve your productivity. And especially for those you who are working on research problems, it's going to reduce the likelihood that you're going to make any errors. Second bullet, Don't be discouraged if you didn't understand everything. I've been working with awk and sed and grep and these other tools for decades now. We covered a lot of material in a pretty short time. So go back, work through these examples at your own pace until you feel like you've truly mastered the content, and play around with it a little bit. Karen had a great question before that I actually had to scratch my head over. That grep question, what if we have the, you know, caret, pair, dollar, anchors the beginning and the end. So play around with those. If you have anything that you're, curious about, mess around. You're not going to break anything. Oh, I should add, you could do all of these examples on the login note. These take, occur in the blink of an eye. It's the kind of things you could do there. And then finally, some of these tools, especially grep to a degree, awk and sed definitely, they are really, really, really complex. You can go much, much deeper if you want to, but I think we covered everything that you're going to need to know. And with that, I think I am all done and happy to take any questions.